Hello everyone, it's April 24th. We get a little bit early today. Well, I'm doing this because I really want to engage in a new data visualization library that I found. It's called Deck. Well, it has a Python wrapper, it's called PyDeck. It allows you to do really amazing um, visualization over maps. And I currently have some data that I want to see on map. Well, technically speaking, the data doesn't have to be shown on maps, but it's kind of just like I want to. Ever since I just start doing Streamlit, I really want to turn every data visualization into an interactive app. I think that will make things a lot more easier to explain. But in this case, I think about the data is actually not going to look any better when I use PyDeck, even if I have a map in the background. It kind of look cool, like, okay, you know where the data comes from. But overall, I don't think this one would really help. I mean, just based on how I'm thinking about it. But anyway, it does not really matter because I just want to do this for fun. So before I get into that, I want to finish LeetCode because I think when I start getting into the flow for that thing, for the PyDeck, I probably won't snap out for a long time. Anyway, let's check this. Somebody commented this. I remember I wrote comment yesterday. Actually, not this one. What is this one? No. Nobody commented on things I wrote yesterday. Ay. Doesn't matter. All right, so today is Saturday. I've been nervous. Critical connections in a network. I've done this using, oh Lord, what's the library's name? Graph Python. What's the, no, GraphVis, no. Create graph. No. What's the one I use? That's not Plotly. It's the, oh man, graph theory. I don't know. I'm just just trying to graph theory. No, that's going to graph theory. Man, what's the library I use for plotting graph? What's the name? Graph network Python. Network graph. Network. What's the library I use? I think I might have it here. Data science? No. I don't see it. Man, I don't see it. I don't see it at all. Holy moly, I forgot what it is. Let's try Google. Maybe it has better luck. So, network Python library. How about this? This, oh, iGraph. That's the one. Yes, I used that to do a lot of graph when I was learning the social network. The social network. It was a good library. I actually kind of forgot how to. Oh, look at this. There's interactions in the background. I didn't know that. Yeah, I think this is the Python iGraph. Yeah, that's the wrapper that I use. It's quite nice. So this is one of the problems that we had in this class, trying to find which link is the critical one. Using iGraph, I think this can be done fairly easily. I'm going to compute some. Oh my God, I forgot already. There are some parameters, right? Some metrics we can calculate based on a graph, like the importance. There are a lot of different values that can be used to calculate the importance of each link, and then just find the one with like the highest importance, something like that. I shouldn't really talk too much about this. Anyway, let's take a look. Okay, connected by undirected server-to-server connections forming a network. Okay. Connections I represents a connection between A and B. Any server can reach any other server. Yes, a critical connection is a connection that, if removed, will make some server unable to reach some other server. Return all critical connections. 1, 3 is the critical connection. Yes. We have 10 to the 5th. And then I is not equal to connection I1, which means there's no self loop, no repeated connections. Okay. Basically, what I think this is I'm gonna do just. Have I done this before? I mean, there are going to be a lot of ends and a lot of connections, right? We have a lot of connections. How do we determine? So, like, if we sever the connection, then we cannot go back. Which means some connections are critical. Like if I have another one here, right? And then these two local, I think it's called clique, something like that. And then they're only connected by one. And if we sever it, then something cannot get into the other. We can start from any one. And then we can visit, right? And then we can visit. They say initially it's all connected, right? I think initially it's all connected. And, ooh, I still remember something. From outside in. Like the, what's it called? Sort. Topological sort. Will this work with topological sort? I don't know. I mean, if anything has one link, right? Yeah, I think topological sort. Topological sort basically, or we can sort based on the number of links a thing has. Hold on, critical connection is a single connection. If removed, it will make, so it's a single connection, right? If we do topological sort, actually I don't even know what this sort actually does. Topological sort, I think what it tells us is just like we pick something and then we lift it up. We can try to traverse from one node to this node, and then we can get it from here. What's topological sort? Of a directed graph, linear ordering of its vertices such that for every directed edge from U to V, U comes before V in the order of the graph may represent tasks to be performed, and the edges may represent constraints. But one task must be performed before the other. But in the topological sort is you just a valid sequence for the task. The graph has no directed cycles. Okay, let's see the example. Many valid topological sort. That's not the one that I was thinking about, right? visual top to bottom, left to right. This is another thing that I've had in mind, but I don't know. Maybe some other source will be more helpful. But this is for DAG. What we have is not a DAG. Every directed edge vertex U comes before V in the ordering. Five, 4. Ah, yes, 2. So these two are there's nothing pointing to them. And then 2, 5, 4, 2, and 3, and 1. Yeah, so 5 to 2, 2 to 3, 3 to 1, and then 0. 1 on 1 order. Yep. No, I don't think this is topological sort though. Critical. So we go from this coming in. I have no clue. I took a class on this, but I forgot it completely. It's critical. That means if we sever it, then something cannot be reached, right? How do we determine that? As we traverse, I mean, we cannot just like keep traversing, right? I mean, if a node can be reached in 2 ways, no. It's if an edge is needed when you visit a certain node, then if an edge is needed when you visit certain nodes, like that's the only edge. So like for 2, to visit 2, we have 2 edge, right? And to visit 0, we have 2 edge. 1, we have 2. But 3, we only have 1 edge. That's why 3 is critical, which means that we cut it, that 3 cannot be reached. But I'm drawing some other graph, just kind of think how can we reason this, right? So if we have 2 edge connecting, but there will always be an edge that has only 1, but critical, okay, critical. Do we have a critical if it's, oh, then it's gonna be empty, right? 4 nodes, and then let's go 3 and 0. Let's put another link, 3 and 0, right? Let's see that this shall return what, empty. Is not a valid type because I forgot to add this. It can be empty. Yeah, so it's no critical. Okay. As we go through, right? I mean, in this case, I'm trying. Do they have like a? Do they draw it further? No, they don't draw it further. It's critical, but it's not counted number of links because this will have like 3 links. This will also have 3 links. It is from message going from here to here, right? I'm gonna start from every single node and trying to start from a node. We're trying to traverse, right? And then into everything. Trying to traverse. We just don't go back, right? And then as we're traversing, what is a critical node? A critical node is in a graph, as that's the single link connecting two graphs, two subgraphs. That is a critical link, right? That's a critical link, which means if we can find anything think. How do we find a link that is, I was thinking like if you traverse, right, to reach each node, I'm going to count how many times the link is hit, right? How many times the link is hit. I mean, ideally, say as you traverse from one node to the other node without going again, right? Every time you go once, right? But no, they're all traversed. No. Doesn't feel right to me. I mean, we have how many? We have a lot of connections. What if we just say break a connection, right? If we break a connection, like we have, say here, we have 1 to 2, we have connection 1 to 2. If we break 1 to 2, then we want to know if from 1 can we reach 2. How do we do that? Well, we need to find neighbors of 1, 3 and 0, neighbor of 2, but they could be like further apart, right? They can be far apart. They can be far apart. And cannot do it. It's 10 to the 5th, so it has to be like ON or something like ON log n, something like that. Man, I have no clue. This one can reach this. So we break, and then we'll try to find out if the 2 can still be reachable. How do we do it? I'm going to say that's reachable by from here. We can traverse. Graph is my weak point. That is for sure. That is for sure. We have a link, and it is not helping, man. This is not helping. How do we find the link? I don't even know where to go. It should be starting from any node, right? And then we traverse. And as we traverse, I mean, we can visit each node, right? Traverse, traverse, and then we reach each node. We can have a path, right? We can have a path from one node all the way to the other node. And we don't want, so that's, but also do, right? If we find a path, we can find a path that can connect every single one. A path, and if we cannot go back, so that's a bad path. And then, so we go from here and here, that's a bad path. Here, here, and then here, here, that's a good path, right? So we do this, that's a good path. Now once we find a path, we can try sever the connection. That doesn't feel right to me, man. If we sever a connection, and we need to know if it's still reachable to everyone. And there could be like tons of paths, right? There could be a lot of paths to connect each one. From any point, right? We have this, and we say we don't know if this is a critical point or not. We assume this link is a critical point, and we assume that this node cannot be reached from myself. Then we try to see if we can reach it. How do we do that? We have to traverse, right? The traverse, and let's say we traverse and we find it. Then we know this one's not a critical link. And then we say we're going to cut the other one, then we have to traverse again. And we say these two are not connected, we cut this one, and we need to traverse again. No, that doesn't feel right, man. That doesn't feel right. Have a breadth first search. From a node, I can go to all my neighbors. And from all my neighbors, I can go, let's say from a node, I can go to all my neighbors, right? And then for my neighbors, I can keep going. And if that going to one of the node on the same level, that means we have a triangle. And that's a fully connected network graph. That means none of those are critical. Does that make sense? If we start from any node and we do BFS, right? Breadth first, so it's spread out. And after it spreads out, I then check every single one that's spread out, and every one can further spread out. If during further spread out, one of the spread goes to a node that we have seen before. Then, like either on the same level or on a level above it. Now let's first talk about on the same level, right? On the same level. It's like here, right? We go ba, 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 3 paths, and then we go take a look at here. And this one, we don't go back, right? We cannot go back. So we take a look at the node that it has, which is 0. And 0 is on the same level. Now this one comes here, and we also know this is on the same level as 2. That means if we have a connection between this, then these 3 are in a triangle. So if in a triangle, none of these are correct, right? None of these are critical. And then we check this is the same and connected 2, so it's not. But in 3, there's nothing, right? There's nothing connecting to nothing. So we say that is a good one. I mean, we can also say we have levels, right? And then we can have a level connecting all the way back to the top. And then we can say we have the top here, here, and whatever links, and then we have a path as well, which means this is not critical because I can go all the way the other way around. So basically what we're trying to see is from the first, whatever we pick the first, and we want to say actually if we link all the way back, then we have like it's not a triangle, but like something here, right? Same with this one, link all the way back to some node here, and on the like previous level. And what happens is from this previous level, we descend. I'm actually might not connecting to this one. Hold on. We have this descend, but there gotta be a path leading to this, like level leading to this, and this one connecting back, right? Yeah, there will be a path. There will be a path. If I go here and this one connecting back, then there will be a path. There will be a path, and during this path, it means it's a cycle, right? If we have a cycle, that means any link in between, any link, if we break it, and that's fine, right? None of them is critical because we're talking about breaking one, right? Not breaking multiple. If removed, will make some sensors unable. So it's just a single, right? I want to test the theory. Yes, definitely it's a single, because if I do both, and then this is a single. It's a single connection. Then none of those will matter, right? If I can connect this node either on the same level or any other level above, then I'll form a loop. Whatever loop it is, I will form. So none of these are critical. If we cannot find, right? If we cannot find, so we have a path down, and like if we can find, that means what happens if we can find? That means none of the connections among those nodes are critical, right? If I have a node connecting to the neighbor or connecting above, then all of them are immune, right? All of them are immune. Then we simply don't consider it anymore, right? Once we find it. We can keep going. Yeah, we need to keep going. So we keep checking. We visit every single one of them once, and we look for a node that do not have any connection to the things above. Okay, let me try on a different example. The example I'm thinking about is we have a triangle here, we have another triangle here, right? That's the example. So I'm drawing on my own paper. So if we start, let's just start 1, 2, that's 0, that's 3, let's go 4 and 5. So we start from 1, right? Same thing. 1, we can go out. Yeah, let's start from 0. It'll be interesting to go from 0 from this point. So 0, and we go out 1 and 2. And from 1, we can go to 2, right? So 1 is fine. And from 2, we can go to 1. That's also fine. But from 1, we also can go to 3, right? So 1 can go to 3. From 2 to go to 1, that's it. The next one's 3 coming out. When 3 come out, 3 can go to 4 and 5. And 3 go to 4 and 5. And cannot go back. 3 doesn't have anything on the same level. And 3 doesn't connect back. So that's why 3, when we look at 3 and look at the things it can connect to, then we know the link is critical. And go 4 can connect to 5. That's why that is not critical. Okay, I might have a solution. It took us a long time to reach this stage. I'm going to just, take a shot. Am I confident? Definitely not. I mean, I'm pretty far from being confident in this sense. But I do want to give it a try. Maybe this is the correct solution. Who knows, right? Who knows? So what we have is, I'm going to turn this into, because these are links. I want to know nodes, right? So from 0, I need to know who it goes to. So a dictionary will be fine. What about the values? And talk about values. Like A and B. What is A and B? I think it should be from 0. So I probably can get away with just a list of lists. Right? So we're going to say graph equals, right? And this for in range n. Right? And then we're going to say for node 1, node 2 in connections. Graph node 1 dot append node 2 and graph node 2 dot append node 1. Okay, so now we have the graph. Then we just pick, I just pick from 0, right? And then we're going to do DFS. We're going to say Q equals this, right? And we're going to say, actually Q is not equal to this. Q is going to be equal to 0, the node. And we say while Q, right? And then we say, what do we say? We're going to find out what node does it have, right? What node does it have? So current node equals Q, the pop, right? So node is 0 now. Now we're going to find out the children of 0, right? And then as we push the children into 0 into it, We also need to know whether 0 has, 0 is a special case, right? 0 is a special, so every time when we check a node, right, we check its next connection, like if it's on the same level or if it's on a level above us, right? How do we know it's a level above us? We need visited, right? We need visited is going to be a set, which is actually going to be 0 has been visited, right? So maybe this is not. This is going to be a set. Let's do set dot add dot add. All right. So I have a node, and then I have a bunch of them. And then when we check each one, we're going to see if this one has any connection to above or to the same level. Right? That's what we want to see, either up or to the same level. If it is not up or to the same level, how do we check if it's the same level? Well, we push it in the next level, and then we check if they are on the same level, or it just means if it has a connection to the thing that we have seen before, except from the one that leading it to it, right? That is the key. That is the key. So, for example, we have 0, right? 0 come out, we have 2 and 1, and we don't consider 0 because that's just the beginning. Or we can just do a dummy node, right? We can do a dummy node and then we'll connect to 0, and then 0 have something to connect back. So 0 will have, so 0 down to 2 and 1, right? And then we push 2 and 1 into the queue, and next one coming out, it's going to be, that's the queue, right? That's the queue. And 2 pop out, we're going to see 2's next, right? And then we go through the node that 2 link to, and then we see 2 link to 0, but that's the one. How do we tell that's the one that's where it come from? We need to know how do we know that's the node that you come from? We need to know where do we come from, which means when we push to the queue, we need to know our parent, right? We know our parent, and 0's parent is none. So let's say we have a parent is going to be none, 0, right? And then visited is 0. And we're going to say parent and node equals this. And we say if, so parent, and then we're going to check, we're going to check its children, right? So we're going to say for child in graph node, right? So we have child in a graph node, and we're going to see if child is not equal to parent, right? If child is not equal to parent, if the child is not equal to parent, which means it's not pointing back, right? If child is not equal to parent, and the child is on the same level, if the child is in Q, right? man, Q is, maybe Q has to be visited. I mean, we already have the Q. Man. Hold on. What I want to know is if there is a way to, so I want to come out, I want to know if my node can reach any of the ones in the current, which means we need a queue and we need a level. I want two things, right? We also, oh man, we need so many things. But that's actually visited, right? That's actually visited. But we haven't visited yet because I'm not visiting this yet. So this is just at this level, right? For child, I am so if a child, oh my god, I feel like I'm almost there, but just if a child, yeah, so 1 and 2 will be in visited already. So if this is its child is 1 and 0, right? If its child is in visited, but it's not the parent, that means it's good, right? And if that happens, then it's good, and then we don't have to put it in. So say if child is not equal to parent and child is in visited, right? Then it's good, right? That's good. Else it's not parent and the child is in visited, which means it's either equals parent, elif, just elif child, child not in visited, right? Child is not in visited, then we're gonna say visited dot add child, right? And Q, no, not Q. Every time we do Q, we have to do a next level equals this, right? So when you say next level dot append, it's going to be parent, which is node and child, right? So we go through everything and we just say, I want to see right? We want to see while Q, then Q out, we'll keep going. Next level, going. Shouldn't we have another one on the outside? I'm confused. Yeah, I think we have a while Q on the outside as well, right? We have a while Q on the outside as well, and then we have basically two levels we have to go. This one is consuming Q, populate the next one, and then next level is going to be here, and then we get every single one out, check its child, and if the child is not, then we're good, and if it is not in, then we push into visited, and once we finish the child, this node's child, so we have a node, and we go through all the child. Once we finish, we're going to see if it's good. So we're going to say has critical equals, let's say false, equals true. Has critical equals true. And as long as one of the child can connect back, then we say has critical is false, right? And then after we're done, we're going to check if has critical. Then that means from this child, right, from this node, from my current node. Hold on. What are we doing? What we're doing is on a node, we're trying to look for its child. And if its child doesn't connect back or connect to the same level, then we say the child, now we say the node and its parent is critical. So we're going to have a result. It's going to be this. So if has critical, then we say res.append going to be parent node, right? Parent node, right? Parent and node. And then after we finish, after Q is all being popped, then we say Q equal to next level, right? Then we go back up. Okay, so as we are doing this, this one is actually, we can use a deck, just pop in the front, but it's fine. So what will happen to the first one, to the 0, right? So 0 comes in, parent is none, node is 0, right? And then 0 has a child, but none of the child has been visited before. So this one will not, so child is not being visited, and coming out has a critical and, so if has critical and parent is not none. Then we do this, and we're going to return res. All right. Take a look. I'm not confident at all. I feel like this is correct, and hope it should be correct. And then the answer is 1 and 3. Okay. And we actually have another test case that we conjured up ourselves. Oh, well, I'll have a 4 in the front. So for this one will give us an empty because we do not have any critical in this one. We can also create another one, the one that I want to do, which is this, and we're gonna add just a few more, right? So what we have is 3 and 4, and 3 and 5, and so 3, 4, 3, 5, 4, 5, right? So we're gonna have 6 nodes. This one should have 1, 3 as well. One, 3 as well. So we use this as well. So we have 3 test cases. 6, this. Oh no. Oh, what the hell? They're not selected, huh? And then this one has 1, 3 as well. Okay. All right. We have n connections. Then this one is critical. N connections. Run it. Dict object has no attribute add. It don't have to be dict. This is not necessary. So it's going to be append. This is also going to be append. they all pass. Okay? I mean, we might get away in this one using a deck, actually. I like to use deck. Collections import deck. And then we'll just say deck equals, no, still Q equals deck, right? And then we just say while deck, while Q. Why I always say while deck? We don't need this, right? And then we can just say equals Q pop left. Then do the same thing. Then we just say not next level. This is going to be Q dot append. Yep. Give it a shot. What I'm afraid is this going to time out, but we'll give it a shot. Pending, judging. Come on, come on. I think we're timed out. Oh, we have a wrong answer. I went and take a look. That's not correct. I think the logic is wrong. I think the logic is wrong. And it's impossible to. You have 10,000. It's impossible to figure out. Expected is nothing. Jeez. What type of graph is that? And I say all of them are bad. Wow. Okay, 1, 0. Let's try it. 1, okay. 1, 0, 2, 0. So 2, 0. 3, 1. Actually, don't. This is 3, 1. 4, 3. 5, 0. 6, 1. 7, 3. All of them are critical at the current point. 8, 5. 9, 8. What's your deal, man? Hold on. Which means as I'm going through, but who connect back to 1? Who connects back to 3? They are connecting to 3. Oh my goodness. This is not gonna work. This is not gonna work. I feel like even if it works, it's gonna time out. Oof. Oh, that's a lot of things right there. And then copy and paste this thing to a new one because we want to correct this. Oh yeah, there's tons of them. 10,000 of them. Yeah, there's no way we're gonna do something like this. We have to find a manageable level that's manageable. It ain't gonna work. 10,000. My laptop's dying. Why is it error? Because it's a 0, 1, they cannot find another one. So if I'm 0, I can visit all of the others. Right, from 0, I can visit everybody. Right, which is fine. And now I visit 1. And from, yeah, I see, because I was just looking at one level. from 1, I was looking at like 3, 6, whatever, that's connected directly to 1. Which, if you take a look here, I think connect to 1 is just 3, 6, but oh god, something's not working. Oh, I have to quit it. Yeah, I have to do it again. And we are not going to test this one because it's just vastly unreasonable. Oh my god. Are you doing this one more time? I'll just close you. Yep. Alright. Yes, the problem is, if you take a look, a 1 is only connected to 3, 6, and 0, right? So when I do 1, its children definitely is not visited. So that's why I kind of I already say 0, 1 is bad. But eventually I think 3, 6 they will connect, they will keep going. So we cannot do immediately. Now what? Now what? Which means we have a very deep, right? From 0 coming out, I have a bunch, and then from 1 it coming out, we also have a bunch, and they don't immediately go back. But it just so happens that as we go deeper, someone linked back. It should be as long as someone linked back that everybody on this path are good. How do we find the child in me? And then if the child is not visited, we'll just keep adding until a child is in the visited. Right? Now I have a child that is in the visited. That means the entire path from the one that's visited all the way to me, and this path is all good. What are these paths? Like, go back. Like, someone has to go back. Right? $53. 53 go back to 1, right? So when we hit 1, we go to 53, right? So when we hit 1, it go out, go to 53, right? And then none of these connects back to, of course they do not connect back, and then they do not connect to each other. And as we keep moving, somebody will connect to 53. For instance, someone will connect to 53. Who connects to 53? Someone will connect to 53. And then when they connect to 53, 53 connects back to 1, right? And then that's good. Which means we just go from 1 to 53, and then we go a layer, then go another layer, and one of the layer, the node, right? One of the node, 53 will go to another one, go to another one, and someone will go back. Well, if they go back, it will be incorporated at the beginning already. So this idea is actually not correct, right? If I start from the beginning and I branch out, I have tons of branches out, and then from each one also branch out, it's impossible for me to go back. Right? Why would I like go back? It's not possible to go back. Because if I go back, and that one will be visited already. Right? If I have a node that I go back, and this node will be visited already. If it's children going back, it will be like, and that will be on the same level. Yeah, so it will always be on the same level. So what type of network are we talking about here? Like a simple solution first. So let's say 0, 1, 2, 3, 0, 1, 1, 3, 3, 2, and 2, 0. Just thinking out loud to see what this one gives us. Yep, there we go. That's a minimum incorrect example for me. So before, yeah, that's the one that we cannot solve right now. It should be empty case. Okay, because from 0, this is just a rectangle. So from 0 out, we go to 1, we go to 2, and from 1, we go to 3, and that's it. So nothing goes back, all right? And nothing goes to 2. So nothing goes to 2, and then from 2, we also go to 3. And from how do we resolve this? Yeah, if we have like a giant, and then from them, we do BFS, and then the next one is 3, right? And then if it already has connection, then we're good. If it does not have connection, then we go to the children, the child, and it will have connection if the child. So all we want to know is if a node has any way to connect to its neighbor, right? If it has direct connection, we're good. If it does not, because I am coming down from top down, right? Top down. If I already have connection to the parent level. So what I want to know is if I have any connection with my neighbors on the same level, right? If I do, that's good. Then there's no critical for me. If I don't, and there are two situations. One is I cannot link back from me going through my child, right? I cannot link back because there's no direct path. Another list, even from a child, I cannot reach back. So we can record these as, say, potentials, right? They're potentially bad, and we keep going, right? We go to the child, and then we have a bunch of potentially bad. Because I can imagine this one just keep linking, right? Linking all the way down, all the way down. And then eventually, somebody will meet, right? So basically it's saying we're branching. So we're branching, and then we just don't see any connection. None of the layers, none of the levels has. I mean, some might have, right? Some might have, and then we can just eliminate all those, but a lot of them don't. Right? A lot of them just hanging there. So we have tons of these that we currently cannot find connection with each other. So eventually, we will reach a level, right, when they do connect. So one is children, and the other is child, right? As a child, and then this child, it connects, right? Some child connect on the same level, right? If a child connects to another child on the same level, then we say their parents are connected, right? And then their parents are connected. And so we just bubble back up, right? So whenever we find a connection, on the same level, then everybody up, right? Everybody up will be connected. Think about it again. We are on the same level. We find a connection. That means everybody leading to them are good. And we have a path from top down, right, leading to this. And we just go from their parents, they're good, and their parents are good, their parents are good. So all of those are good. So it's these links are good. Right? The links are good. So every time we find one, then the link, that we save all these links, the link from here, go to this child, that's another link, that's another link. It's like going from, oh my god, from top down, I have all these links, and then we have a link. Every time we visit a child, there'll be a link connecting to it. There'll be a single link connecting to it. Because if there's another link connecting to it, then we have a circle, then we're good, right? So from top, we have the single link to this child. And this child, if we have anything connecting to another one in the same level, then those links do not continue. Otherwise, the link continues, right? Continue until we find one that connects. Once they connect, then their child will start from a new link. That idea might work. So go back to this example, right? So 0 to 1, we have a link, 0, 1, right? And then 0 to 2, we have a link, 0, 2. And then from 1 there's no cross-link. Therefore, from 1 go to 3. When we reach 3, 3 has 2 links, 0, 1 and 0, 3, right? And then from 2, I go to 3 as well. And from 2, I go to 3 as well. And then from perspective of so on 1, we push 3 into it. From 2, I don't push, because from 1, I push 3, and every time I push, I already put it in the visited. So next child, so 0 gets 1 and 2, right? And then 1 gets popped out, they put in, and then 2 gets popped out, and 2's children, I see it is already in it, right? It's already in it, which means it's on the same level. And then 2 does not push it in it, right? So when 2 goes to 3 and we don't push it, but 1 does push it to 3. And then 3 comes out. And when 3 comes out, 3 has link 0, 1 and a 1, 3. Right? That's when we push 3 in, because, well, why do you push 3 in? No, that's fine, yeah, 3 in. So when 3 comes out, I'm a little bit confused. So 0 push into 1, and this is a child, right? 0 will have a child as 1, and then every time we have a child, we need to see if the child has been visited. If the child has been visited already, then we have a loop, right? And then what do we do? If a child has visited already, if a child, because it's only be on the same level, right? So I have a child. In this child, so we have a child, and we're considering this, right? On the same level, we have this, and if it has a child that has been visited already, then that child we don't continue. Yeah? Yeah, that child don't continue because it's on the same level. It's been visited already. But what if we visit that child? That child has to keep going. Yeah, because we finish a loop here, but that child has to keep going. So that one has child. It's fine. So it has a child. So here 1, right? 1 we have a child. And when we see 1 has this child, it has not been visited before. So we put this in, right? We put this in, and 2, we have a child. We should put it in as well, right? We should put this in as well as the next level, right? This is visited. But you're saying here like 2, we just don't push it because it's in already. So from 2, we don't push it. So there's no more from 2. There's only from 1. So from 1, now we go to 3. So from 3's perspective, it does not have child, right? So, I mean, 3 does. 3 has 1, but 3 has 2, right? Yeah, so from 0 to 1, 0 to 1 and 2, and then 1 will go to 3, 2 does not go to 3, and 3 sees that a child is visited. Hold on, why would this one give us... We start from 0, right? And then from 0, the child is 1 and 2. And if it's 1 is not being visited, so visited only visit 1. Q.append. Or 0 and 1. Alright? And then 2, so it'll be 0 and 2. And back up. The parent kernel is none, so we can do it. Back up. So this is 0 and 1. The child is not 1. 1's child is 3. 3 is not, so we visit 3. Right? And then Q.append is 1 and 3. And that's it. Coming out. Critical is false. Right? So, but now what we say, we hold on to it. We hold on the path. And then we'll go to 2. Right? So we'll go to the next one. 2 will come out. 2 will come out. 2 will have a child. What's this 3? 3C is already visited. Right? So that means from perspective of 2, we already formed the loop on the 2. So we don't visit 3. Right? So now come back to 3. 3 pop out. And 3 has 2 child. Right? 3 has 1, that's the parent. And then 3 has 2. And then 3, take a look at 2. 2 has been visited before. So from 3's perspective, I have also reached. So that's the end. There'll be nothing in the result. What will happen when we have the result is we have one path all the way down, and then we go to a node like this continuously. There's nothing, right? So thinking about here, right? This path is just 2 to 1. That's a path. That's a link. 1 to 3. That's another link. And from 3, there's nowhere to go. So are you saying everybody on this link has any trouble? That's not technically true because 1, 2 is not a critical link. Like when somebody, so like 0 to 2, 0 to 1, right? And then from 1, we go to 3. From 1, 2, already is. So we just remove, right? So like the history of this gets removed. But when we remove the history here, this one still contains the history. It contains, so from 1, right? From 1, we can go to the next one. We can go to the one that's contained inside. And we have a path towards 1, right? We have a path towards 1. And from 1, we have children's. And then we need to go through 1's children, find one, right, that has been visited before. And if we can find one that has been visited before, then all of his children will start fresh. If we cannot find one that started before, then all of the children have to carry the same weight, carry the same path, right? So they'll all carry the same path. It's like one path and then branch out, then every single one of them will be critical. This will be critical, this sever it, yeah. But if later on, right, then this child is become visited, then are you saying all of their paths from top to bottom is becoming good? No, it's still not. It's still, as from that node's perspective, its child is on the same level, right? That actually depends, right? That depends on, so we just have, if it's on the same level, right? If we're on the same level, it depends on where that thing come from. And that can depend, oh my God, this is not helping. Let's take a look at a hint. We're gonna, I might have heard of this name. Tajan, strongly connected components algorithm. Strongly connected, find strongly connected components of a directed graph. Runs a linear time, matching the time bound, blah blah blah. Takes directed graph as input and produces the partition of the graph's vertices into the graph's strongly connected component. Each vertex of the graph appears in exactly one of the strongly connected components. Any vertex that is not a directed cycle forms a strongly connected by itself, a vertex whose in degree and out degree is 0, or any vertex of an acyclic graph. Okay, let's take a look. So this one goes here, goes here. That's one. Here, goes here, here. Okay, so basically use this algorithm to find the strongly connected. What do you mean by strongly connected? If every vertex is reachable from every other vertex. Ah, yeah. We find the strongly connected, and the two, every vertex is reachable from every other vertex. Isn't the entire thing is? My lord, that's long. That's a strong. That's fine. Another implementation. If there is a path between all pairs of vertices, a strongly connected, a directed graph, the maximum is strongly connected. For example, there are 3 strongly connected graphs. But ours is not strongly connected. But like if you run the algorithm, shouldn't it be everything will be the same? Let's see, what's the illustration of this approach? Initially, what is this? Traversal. That's not helping. That's not helping me. But disk and the low values relate to both directed and undirected graphs. So in both pictures, we take an undirected graph. Okay, what is one DFS? Tajan. DFS search produces a DFS tree for strongly connected components from form subtrees of the DFS tree. That's true. If we can find the head of such subtrees, we can print store all the nodes in that tree, including head. That will be one SCC. Okay. There's no back edge from one SCC to another. It can be cross edges, but cross edges will not be used while processing graph. To find the head, we calculate disk and a low array. Low indicates earliest visited vertex, minimum discovery time that can be reached from subtree rooted with U. A node U is head if, what's disk? Is the time when a node is visited first time while DFS traversal. Okay, we have shown a graph and it's it's one of the DFS tree. There could be different DFS trees on the same graph depending on ordering which edges are traversed. In DFS tree, continue arrows are tree edges and dashed arrows are back edges. Ah, so this one is back edges, and it doesn't matter back edges or not. So disk is the time the node was first time. Low take us forward from ancestor node to one of the descendants. And node C, so okay, so this is all one. So this is one step. How is A is one? It's just time point. 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 4. Oh no, so 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. The first time they are visited. And low is to one of its descendants. For example, from node C, tree edges can take us to node G, node I. C is here, can take node G and node I. What? From ancestor node to one, for example, from node C, tree edges can take node I, node J, okay? Back edges take us backward from a descendant node to one of its ancestors. For example, from node G, like E, C, A, right? But not D. It's EC. If we look at both tree and back edge together, then we can see that if we start traversal from one node, we may go down the tree via tree edges and then go up via back edges. For example, from node E, we can go down to G, okay, and then go back to E, and then up to C. Okay, oh, I forgot. This is E, G, yeah, to C. Where am I? Similarly, from E, we can go down to I or J and then go up to F. Low value of a node tells the topmost reachable ancestor with the minimum possible disk value via the subtree of that node. So for any node, low value equals to its disk value anyway. Let's read that sentence again. Low value of a node tells the topmost reachable ancestor via the subtree of that node. indicate the earliest visited vertex that can be reached from the subtree rooted with U. The earliest as 1. Okay, C as 1. D is 1. E, well, if we keep going down, earliest from E can reach is 3. As C, E can reach C. So only one back, right? Is that what you mean? There's only one back. F is also C. G is C. H can be pointed to F. I to F. J to F. Read that again. Low U indicates earliest visited vertex. Okay, earliest visited vertex. The vertex with minimum, that's called discovery. The with a minimum discovery time that can be reached from a subtree rooted with U. From a subtree that's rooted. Okay, so we rooted at E, and then we're gonna go from E, which will ignore everything that's going to E. E is the root. So we can go to F, and then go to G, and G will go to C. Is the previous, is the earliest visited vertex that can be reached from subtree. I mean, we cannot say from this one, well, everybody can reach A. Okay. Tree edges takes it forward. Back edges take it backwards, right? If we look at both tree and back, we can see that if we start traversal from one node, and go down the tree, and then go up via back edges. From node E, we can go down to G, yes, and then go up to C. From E, we can go down to IJ, and then go up to F. E, we can go down to IJ, and then go up to F. So we only allow one up, right? It means only allow one up. Low value of a node tells the topmost reachable ancestor the minimum possible discovery value via the subtree of that node. So for any node, low value equals to its disk value anyway. A node is an ancestor to itself. Then we look into its subtree and see if there is any node which can take us to any of its ancestor. If there are multiple back edges in subtree, which take us to different ancestors, then we take the one with minimum. If we look at node F, it has, if we look at node F, it has two subtrees, subtree with node G and subtree with node H. Take us to E and C, right? E and C. So it's just its subtree. That's the root of a subtree. Let's see what the subtree can take us. The other subtree takes it back to F only. Here, the topmost ancestor is C, reaching, so low value of S is 3. Based on above discussion, it should be clear that low values of B, C, and D are 1, as A is topmost. For any node U, when DFS starts, it will be set to its discovery first, then later on DFS will be performed on each of its children V, one by one. Low values of U can change it in two cases. Case 1, tree edge. If node V is not visited already, then after DFS of V is complete, then minimum of low V and low U will be updated. I don't understand. Jesus. I'm lost here. Oh no, I'm lost here. For any node U, when DFS starts, low will be set to its, what does it mean? Disk first? Discovery first? Then later on, DFS will be performed on each of its children, V one by one. Low value of U can change. I think it says low value as itself, and then low value can change in two cases. If node V is not visited already, then after DFS of V is complete, the minimum of low U and low V will be updated to low U. Well, if V is not visited already, then we're going to visit V, and oh yes, this is correct. This is correct because V might get to a node further back than U, so we should update low U with low V. It's true. Back edge. Child V is already visited, then that's a back edge. The minimum of low U on disk V will be updated to low U. That is also correct. Case 2, can we take low V instead of disk V? Answer is no. Okay, we take low disk V, discovery V, yes, and low U and discovery V. Can we take low V instead of disk V? No, because we only allow one back edge. Yeah, because if we take low V instead of discovery V, then, because low V is from V to going back, right? From V to go back. So that is not, I think this probably say that's not a subtree rooted there. I mean, all I can say is you are only allowed to take back edge once. I mean, otherwise, I don't know, because you cannot do 2 times. You're only allowed to do 1 time. Back edge, tree edge, forward edge, cross edge. Oh, some low and disk value help solve other graph problems. To track the subtree rooted at head, you can use a stack. Keep pushing node while visiting. When head node found, pop all nodes from stack until you get head out of stack. To make sure we don't consider cross edges. When we reach a node which is already visited, we should process the visit node only if it is present in stack. Else ignore the node. I don't understand the last part. But what it's saying is we do DFS on each node, right? We do DFS on each node, and in its children, the children, if it's not visited, we do DFS on it. If the children is visited, but like in this case, I mean, in this case, it's a legitimate, like which one is the critical, and there's no critical in this one, but that's what we produce, right? I mean, everybody is a back edge. How do we use that? I mean, we can just go, right? Go, and then this one, we have connecting here. That's also all connected, right? All connected. Connect also back. So if we connect back, then the low value of this will become 1, right? The low value will become 1. And then we also connected this, and this one connects back. And not visited before, this will be whatever this one the value is, and this one will connect back. It's children, so this one, the low value will also be 1, right? The low value means all of these can connect back. So basically we use low value, we can find a node that they can all connect back to. Right? They can all connect back to. So isn't that the thing that you're thinking about, like the one thing that everybody can connect back to? So once we can connect back to a node, right, so like all of these can connect back to, so we can say all of these can be reached. There's no critical among these. And then C can go here, right? We're going to go here, we're going to go here. And then from this one, we say this, okay, put it here. And I mean, we have to go here, right? And then this one can go here. And then this one reach back, right? This one visits something that has visited before, right? So this, but actually, because we are all going this way, so this actually, when this one goes, go here, that's visiting back. And go here, this one visiting back. And then this one just keep going, have 2 ways to go, like this way and this way. And then from here, it hasn't visited this before. So we go here, then we go here, right? And then this one already visited, right? And then say this one connecting back. How does that help us? I don't know how this one helps us. Like this, I'm kind of trying to think that all of these are just an edge, undirected. All right, so from C we can go to E, from C we can go to G, but it's DFS, so we go to E, and E we can go to F or go to G, right? It depends on which way you go first. Let's just say we go to E, then E go to F, then F go to H, right? H go to I go to J, and J go back to F. So now J has this, right? And this one also pointing here. How about H? Well, H, we go here to see this pointing here, so this H definitely are pointing to this as well. So now all of these are pointing here, right? All of these are pointing here. They're all pointing here, and this one can go G, right? And then from G, we can go E, right? And then from E, we already visited. And then from G, we can also go C. So G want to point back to C, right? And then, which means F will also point back to C, right? F also point back to C. Okay, now what? So we have the low value, which means these are the nodes that everybody can connect back to. C can go back to A, F can go back. Right, so we say E, F, G, they all go back to this. These can all go back to here, which means we have a loop. We have like all these can go back here. So you're telling me like the critical points are these are the critical points. It still doesn't solve the problem. I mean, this is just to find the strongly connected components. Strongly connected components. How does that help us? From 0, we can go to 1, and from 1, we can go to 3. From 3, we can go to 4. From 4, we can go to 5. From 5, we go back to 3. So we say 4, 5, they all link back to 3, right? Because there's only one run, right? The 4, 5 all go back to 3. Right, it's child. 5, its child has been visited before, so it's the minimum of the 3. No, it's 3. Discovery 3 and a minimum of discovery 3 and the view itself. I have to visit it, and then it's going to be the child. Use this. This is the tree edge, minimum view, and the minimum this, right? So this will become, they are all rooted to 3. So we know 3, 4, 5 are rooted to 3. And then it's done. So 1 rooted to 3. And 3 is a tree edge, so just it'll be itself. At anyone, the low is just itself. Then so 3, the low is itself, just like here. 1, the low is itself, right? So 3, the low is itself. So that's the head, right? 3 is the head. Because using this, we can say tree edge. So from 3, we go to 4, right? And then when it's done, 4 pointing back to 3. And 3, well, so 3, the low 3 is still 3. And then we'll go to 5. 3 go to 5. 5 is already visited. Now, low U and 5, that's terrible. So it's going to be 3. So 3 is a head. 3 is a local head. 3 is a local head. And then 1, I have to visit 3. Because 3 is an edge I haven't visited before. So we're going to be the low U, low 3 is 3, and low 1. Low 3 is whatever the value it is, and low 1 will be whatever it is, and then we can take, basically, it's actually going to be 1 itself, because 3 doesn't go back. And then 1 will go to 2, this is 100 before, 2 will go to 0, right? The 0 is visited, right? So it's going to be discovery, it's going to be a back edge, right? It's visited. So we're going to be discovery, that's going to be 0, right? So 2 will be 0, and then 1 was actually going to be 0, right? So we find 0 is another 1. It's not 1, it's a 0. 0 is another head. Right? 0, because it's back to 0. So 0 is the head. So 0 is the head, and 3 is the head. So basically we're saying whoever is the head, right? 0 is the head, 3 is another head. So whoever is the head needs to well, like a link between it and whoever linked to 3. But then 3 have many links, right? Has many links. Let's say 1, 2, 3. A back link. If we always go from small to large, right? From each node, and we always go small to large, and from large to small is always a backlink, right? Then if we find an head, that means everything under it is like we traverse, and then we find something, we go back, right? So one link go back, right? So that's the path, right? We'll have a node, and we traverse, whatever traverse we do, and then eventually something link back. And once it link back, and update everybody, so they all link back to that one, right? They all link back to that one. Now that one, if it also links back, right? If that one is not a head, which means it also link back, that means it's not a critical. It's not a starting point. So we need to find the head. And the head will be like nothing goes to it. Yes. What does a head mean? Head means nothing goes to it. Head is the head, right? Nothing goes to it. So that's the key. We need to find the head during a DFS. During a DFS traversal, we can find the head, right? And then we pick the head. Then the link is the head goes to something. But what exactly is the link? Right? What exactly is the link? I mean, we have a head. We know that nothing goes to the head. The head is the start of the current, whatever it is. Right? Who goes to the head? Now we know when we find a head that from that node, when we traverse, it always goes to the bigger ones. So it's only going to be the one that's smaller than it. That's the node that link to it. But if there are 2 linking to it, then are all the nodes that's smaller than the head, are they going to be all considered as critical node? So if it's a head, right, the criteria of being a head is nothing, it cannot reach anything before it. Right? That's the criteria. That's the criteria of being a head, is from whatever traversal from the head, it cannot go to anything before it. Right? So if there's any link, right, from a node before my current node that towards me, then that is a critical link, because there's no other way for me to reach that, to reach above me. Yes, I think I know how to use Tarzan. This is not correct. We need to keep this, right? And then I'm not looking at the implementation, so I'm trying to solve it myself. We're going to use DFS, right? So we have a node, right? And then we're going to have two things. We're going to have a disk. Disk is going to be 0 times n, right? And then also low is going to be 0 times n, starting is all the same. And then we have a node, right? We have the node, And that's it. DFS is just a node. I mean, we need visited, right? We need visited equals just a set. And this one doesn't return anything. Okay. So we can sort it. That will be better. Anyway, so we're doing a node, right? So a node is not visited before, so we visit a node, and then we need when we visit a node, oh, we need a count. Yeah, we need a count. So we need a step. Step is going to be int. Node is actually going to be int as well, right? So we have a step. So we have a step in. I'm going to do disk node equal to step. Right? Whatever step that it has to take. Yes, whatever step we have to take. And then after that, we need to check its children. So for child in graph node, right? Check its children. If its children has been visited before, right? If child in visited, and then of course visited dot add node, right? If the child is visited, that means it's a back edge going backwards. So we can say when we first visit, right? We're going to say this and a low node also equal to step. When we first start, when we first visit a node, that's the case. And if child has been visited, right? Then low node shall be the minimum of low node itself and the child. But the child has to be discovery child because we only allow one back edge, right? And they'll group together. That's like a whole group. If we need another one, and that just mess things up. Only one group, one back edge allowed. Else, if child has not been visited, right, then we're going to do DFS child step plus 1, right? DFS the child after finish DFS, then we're going to upload node. It's going to be minimum, my low, and my child's low, right? And then we end, right? We terminate. Now we're going to do DFS. We're going to start from 0 and 0 step. That's what I like. I like 0 steps. And after that, the disk and low will be populated. I'm actually going to take a look. No, you can just keep going. Now we want to find out the head, right? The head. So we just take a look on going through disk and low and see which one is the head. It has to be disk and the low will be the same. So we're going to say for I in range n if I, disk I, is equal to low I, and I is not equal to 0, because we start from 0, cannot count 0. Right, then that is a head. That is head that we have to take care of. Now with the C, right, then we can have a result, right? Then we just see all the nodes that's smaller than me, that's connecting to me. So I'm going to say, I don't need to sort, we'll just go through, that's fine. So we just say, for pre in graph I, if pre is smaller than I, then rest.append pre, right? And we go through all this. Now we're going to return res. Run it. Dict has no add. Visited is a set, not a dict. Now we pass this. Let's try these. We fail on the first. I think it only returns empty set. Okay, that's fine. That's fine. We take a look at what we have. So we're going to print disk and print low. Okay, something is not correct. I think that's this one, right? Take a look. So we have from 0, right? So 0, and then we go to 1, right? And from 1, we go to 2 and 3. Okay, the discovery is fine. Now they all connect back to 0, right? But 3, the 1 can connect back to 0, so 1, right? And then 1, go to 2. 2 go back to 0, that's a back edge. And 1 go back to 0. True, this is all correct. But 3, from 1 we go to 3, right? And while I am at 3, my low node shall equal step. It shall be 2, right? And then the child. Oh, it cannot be parent. It cannot be parent. Yeah, because I am taking into account the parent. No, like the back edge cannot go directly back to the parent. How do I enforce that? We'll have to do a parent then, right? We'll do a parent. So parent, parent, a node. Parent is going to be int, right? And then if child in visited and child is not equal to parent, then we do this. Else, actually, if child in visited, no, and this, if child not in visited, then we do this. So if child is equal to parent, then we don't do anything. And when we visit this, it's going to be child, right? That's the current node. Parent is the node, right? Parent is the node. And that's that. So DFS, I want to just pass the -1. Right? That's its parent, whatever it is, right? And let's try this one. Now we pass, right? And I'm going to try all these. They all pass. I want to try the big one, the giant one. This one. Let's see if it can run. Judge and finish. Take 336 milliseconds. Take a look. This is based on the hint of using Tajan's algo. All right, let's see if this one passes. Pending, judging. Come on, come on. Oh my God. Oh, it's accepted. How long does it take? Oh, wow. That's not bad at all. Why am I laughing? I didn't solve this. I need to give it like, it should be success, fail, and this will be like cheated. This is cheated. Well, this is not my solution. I didn't come up. I did not come up with this all by myself. I got stuck, and the hint suggested that I take a look at Tarjan's article, which I'm going to link this article. I mean, it's good, right? Tarjan's article, not Tarjan's article, just Tarjan's algorithm. The central point of Tarjan is that we find the head of a graph. We find the head of the graph. The definition of a head, in a graph is that is a node which how should I say it, which is the is a root of the subsequent is a root of the subtree that this node does not connect back. This node does not connect. Is has in a graph head. Definition of a head inside a graph is a node which does not have any back edge towards a node that has been visited before in DFS. Yes. In other words, a head is the root of a subtree inside a graph. Subtree, subforest, whatever you want to say, inside. It's actually a subtree inside a graph. From the head, we can only traverse forward. We cannot traverse backward, not counting the edge leading to the head. We cannot traverse backward on other edges. So in this problem, Tarjan is used on directed, used on DAG. We can apply, although our graph is undirected, we can simulate it as a directed by traversing from small node to big node, right? In other words, a forward traversal is follows an edge going from a small to big node. A backward edge is from a big node to a small node. Using Tarjan, we create two arrays. One is called disk, discovery, and the other low. The lowest node that can be reached lowest node that can be reached with one back edge. It is important to stress that only one back edge is allowed to traverse backward when computing the low array. Yeah, only one can be allowed when we're computing the low array. Once we finishes DFS, we populate the disk and low arrays. Right? We populate these two arrays. We the ith value in, let's just say disk I. Disk I is the number of steps needed to reach I in the DFS. Low I is the most previous node, right? The most previous node is actually not the most previous node. It's it's not it's the step, is the number, is the step to reach the most previous node. Is points to the value of disk J, where J is the most previous node reachable from I using one back edge. One back edge. Ahead is a node K, where disk K equals low K, which means from node K we cannot reach any other node before it. Our goal is to find all the head node K in the given graph, and the critical edges are the edge connecting directly leading from a smaller node to K. Runs an ON. It's actually, the DFS is ON, and this is, check everyone, actually is a lot longer than ON, because because we have to find it, and then we go through the nodes. Actually, I shouldn't say, I don't know. This is complicated to calculate this. I just say the runtime. Runtime gets us 2188 milliseconds. Surprisingly, give us an 89% ranking. But it's pretty hard. I mean, admit it. I don't think this is a. Yeah, this is like a hard question. I'm pretty sure this is a hard question. This is a good article, though. I shouldn't say this. It took me a while to understand. I thought like I've done something like this before. Like, how come this is a hard? Like, I don't understand. But yeah, it's a hard one. I bet there are better solutions than this. Oh yeah, I've done this before. Oh my goodness. Oh, I hit a better. Wow. No way. I started at 21, right? Couldn't do it. Just couldn't do it. And then tried it again on 25th. Couldn't do it. I think I gave up. I did it. Tried it again. What language? All Python. And 2 years later. Yeah, I think this is. I think it's probably just for fun. Like, why did I do that? I don't understand. All right, done it before, but can't do it. DFS detailed. Ah, I remember this question. All right, let's take a look. Find out this theorem on a connected graph. An edge is a critical if and only if it is not in a cycle. Yes, yes. So if we know how to find cycles and discard all edges in the cycles, then the remaining connections are the critical edge. That's true. How to find edge in the cycle and then remove. I kind of bring back memories. Bring back memories. I already liked it. See? I bring back memories. We find edge. We find cycles. If we go back to a node that has been visited before, then we have the edge. And then we not have the edge. Then we have a cycle. So whether or not an edge is in a cycle. If we DFS, and then we go back, we hit a node that we've seen before, and then those edges are all not good, right? Define rank of a node, the depth of a node during DFS. Oh, that is the disk discovery. Only the nodes on the current DFS path have none special ranks. In other words, only the node that we've started visiting but haven't finished visiting have ranks. Or have started visiting but haven't finished it have ranks. If a node is not visited yet, it has a special rank. If we fully completed the visit of a node, it has a special rank. How can rank help us removing? Imagine you have a current path of length k during. Yes. The nodes on the path has increasing rank from 0 to k increment by 1. Surprisingly, you visit next finds a node that has a rank p, whereas before. Why does that happen? You found a node that is in the current search path. That means congratulations, you found a cycle. Yes. But only the current level of search knows it. How does the upper level of search knows it? If you backtrack, the return value returns minimum rank it finds during the step of search from node U to neighbor V. If this returns something smaller than equal to the rank U, then you know this neighbor helped it find the cycle back to U or U's ancestor, so U knows it should discard the edge U to V, which is in a cycle. After doing DFS, all edges in cycles are discarded, so the remaining edges are critical. How do you discard again? DFS of back depth dot discard. And discard, we have to write a discard. There's a function called discard. Node and neighbor. Oh, it's this plus this. Yeah. We have using rank, pre-ordering. One array. The rank is very different from max rank. Result by collecting non-critical edges after the DFS in the current search. Okay, it's still slightly different from my understanding, right? What I did is two arrays, and then we find the low, and we find a head, right? So I'm not making any, I'm not removing anything. I'm not removing anything. I'm just finding the head. And after I find the head, I declare that the ones connecting to the head are the critical edge. He uses rank, right? So as we go through, we'll increment the rank, visiting or visited. Rank, then it's larger than 0, then either visiting or visited. So initially it's a -2. And then I put a depth, so that's rank is depth. Main back depth is n. And then we'll go for the neighbors. If rank the neighbor equal to depth -1, that's the previous one. Special value in case depth equals 0. Right? That's depth -1. That's your parent. Continue. That's why I have to pass parent as well. And then back depth equals DFS neighbor. So the neighbor and depth +1. So I want to know the back depth. Yes, the back depth. And just like when we hit someone that's smaller than me, right? And then we say the back depth is smaller than my current depth, which means for my neighbor, I can go to a node that's smaller, right? Smaller. We find the minimum depth actually. Yeah, we find the minimum depth. And then if it's smaller than the depth, then that means from node to my neighbor. Yeah, from node to my neighbor, and it can lead to something. So it's in a cycle, so I can remove it. Okay, and then the main depth of me will be the depth of my child. So as from a node, I go to my mini child, and they can all go back. Right? They all go back if they can, and then I just pick the smallest one of them, and that means this is where I can go if I want to go back. Right? And then rank node equals to n, and return minimum depth. And as it goes through, it's discarding, right? It's discarding. And didn't even consider this needs time as well. Oh, but it sets it to map. That's why, but it needs time to do. That's OM. Ah. Okay. I see what you're doing. That's using rank to find. Very well. Tarjan. So, if you want to do Tarjan while doing this, how would you do it? Well, I would say I can do it here as well, right? So, if child in visited, yeah, if a child is visited and it's not a parent, that means that's a loop. Yeah, we have a loop, right? So from a node to child, and the child is, then from node to child, like we go back, so from a node to child, that is, so from a node, I have a child going back, right? Then that link is in a loop, so I can just discard it, right? And I still record. Do I still record? So I go back, right? And then if I go back and go from a current node, then I go backwards, right? I go back, and then I say this node I deleted, right? How about my parent? Like if I go here, if the children have not been visited, I'll visit it. After I visit it, then I need to check its node. Yeah, it's low. I check it's low, and yeah, check it's low, and the low will tell me uh, which one that it has done before, right? The child. So like if I can return, I need to return. What do I need to return? I need to return the earliest node that I can return back to, right? So if I can return back to this node, then just return that value. So I can say here, I can return the load of the child, which is the earliest I can reach. And then I compare these two. So the load of the child is the load of my current node, right? The load of my current node. Load of my current node is which one I can reach. And I go through every one of them. If I can reach, but I keep going until I find the smallest. And then I just remove it. If it has visited, I remove it immediately. If it has not been visited. If it has visited, right, then I can just go say low node can equal to discovery child. But now in the current case, it's a loop, right? It's a loop. So I can actually say low child. It's fine. I can just say low child. I mean, it's different from Tarjan now, right? I can just remove it. But I'm going to update my current low node. I mean, as long as my low node is, now I need to know where is the earliest node I can go back to from me. But has to be disk child though. It has to be disk child. Minimum depth, right? The minimum I can get back to from the DFS, right? From the child. Each child we can go back, and it depends if we have visited or we have not. And if we have visited, then trying to find like the difference between these two. We have steps, right? And then what we're doing is every time visit a node, we increment a step, and then if we find a node we have visited before, we just need to know how many steps it takes to reach there. And that's the disk, right? That's the disk, is how many steps it takes to reach there. And once we find that, we remove the link, so we know the child is go back. It's a loop, so this one we don't need anymore. So we remove this, right? We remove this, and we say from my current, the earliest I can find is this, right? And then we go to everyone. So we find each node, the earliest node I can reach back to, right? The earliest I can reach back to from one back edge. The earliest I can reach back to. So I know this, and then here, everyone, if it's, yeah, that's, I think I'm going to implement this one more time. Graph and mark the order. This records how far, but I'm going through, you must something mark the lowest order of the node that can reach. And every time you find it, you can remove it. Main of the current vertex and next ranking. And one connecting. I'm currently stuck in this, so I will try to use that person's solution for this. Yeah, this one shall be in the hell. At the list, no, nightmare. This is a nightmare. But even if it's nightmare, we are going to do another solution. It's expected, right? I know yesterday I said today might be hard. It is hard. Okay, so we're basically going to copy and paste almost the exact same thing, but just with minor differences. So I have the graph, right? So we're going to call it the we can reach back. That's just the low. The lowest we can reach back. No. We're going to return value is the lowest we can reach from each one. And then what we're going to do is just steps. Discovery. Yeah, let's do discovery. Right? And we do visit, which is fine. And we need to turn connections into when the connections, when you remove connections into a tuple, right? Into a tuple. How do we turn that into a tuple? Result? No, it can be a set. Res.append dot add. We're gonna say min and 1 and 2 and x and 1 and 2, right? Now, now step, right? So we're gonna do is no equals this. That's good. We don't need this. Visit that is good. So child and child. If child ain't visited and child is not equal to parent, right? Then we say, what do we say? So it's visited, right? So we say min step. The back reach, right? Back reach can be n, right? So if child is visited, then we say back reach equals min back reach and discover child. And when it happens, well, honestly, that's actually not how it's going to be, because I think if child in visited and child is not equal to parent, right? Then we say child back reach equals disk child, right? Else, if it's not visited, then we are going to return child back reach equals DFS. No, child step plus 1. Yep, right? After we go through, then we have child back reach. We say if back reach, my back reach, no, if step, current step and reach me is smaller or equal to child back reach, right? Which means the child can either reach myself or it can reach higher. That means loop, right? Then we can remove. I'm going to say res.remove from me to my child, right? So remove from me which one is me? Node, that's me, node and child, right? So we're going to remove this. And back reach, my back reach, actually, why do you do a hyphen? Back reach can just, yeah. My back reach is equal to min back reach and child back reach. Once we're done, we're going to return my back reach, right? Child in this, I can just say if child equals parent, continue, right? And then I say back reach this, if child in visited, else, I'm going to do this, DFS. Now when you change the name, the child back reach, and there's a back. All back reach can be back. Right? Back. This is the earliest the step where the earliest node can be reached. Hard to explain what this back is. Back is the number of steps, right? The number of steps. The number of steps to reach the earliest node reachable from the current node. Not even sure if this explanation makes sense. So if it's equal to parent, then we don't do it. Otherwise, child back is equal to basically child if child isn't visited. Else equal to this, right? And then run this, and then we come back. And we're going to return list rest. And that's it. Right? So into solution 2. And it's because I haven't deleted this one. I don't use this either. Fail. Okay, that means my understanding is not 100% correct. That's fine. Let's just take a look. I think I included everything. Nothing is removed. Nothing is removed. Step is smaller equal to child back. But have we even hit here? I don't think we hit here. No, we haven't even hit here. Why is that? So this node, you always equal to step, right? And then we keep going. Back is n. And then for each child back is going to be if child is visited before. Else we're going to do DFS, right? We'll get the child. And after this is done, we're going to check my current step. If it's smaller, oh, how? No, larger equal. Actually, we're going to do even better. Child step is smaller equal to current step. Wait, what the hell? Right? Child back. How come both? Something is not right. What the? Oh! My God. I forgot it's called DFS. We have issues. Key error. Oh, yeah. So, node and child has to be min node child, max node child. Yep. And then this has to be not like this. It's gonna be actually that's fine. List R or R inverse. Yep. There we go. Yep. I actually like this one better. It's cleaner. Visited, result, remove loop exists, right? Can remove current edge. I'm pretty sure even if I return a list arrays, it shall make sense. Anyway, so I'm going to write something here. This is a reproduction of the answer in this post. I'm pretty confident that this one will work. All right, so here it has similar sense as Tarjan, but better. But I think is better suited for this problem. Basically, we DFS, and if any node can lead to a node that has been visited before, any child, right? Any child can lead to has been visited before, then we are confident that there is a loop that the edge from node to child, current node to child, is in a loop, and it must not be critical. We remove it. And that's it. That's the essence of the solution. Very neat. I like it a lot. So we're going to do... I am not going to memorize all this. What I think I can do is, I mean, the idea is quite neat. You should be able to figure it out. Right? You shall be able to figure it out. That's about the same time. That's okay. I mean, you shall be able to figure it out. Basically what it does is just to detect, right, whether a loop exists. If a loop exists, we simply remove the edge. All right. We're gonna change today's title to cheated, but we did do it. Took us a long time, almost 3 hours, but it's it's Saturday. It's good for a little bit brain exercise. All right, that'll be it for today. I'll see you guys tomorrow. Adios.